Welcome to our forensic glass analysis lecture. Please watch this lecture in its entirety because there's going to be stuff that, one, you're definitely going to want to know. Two, I'm going to do some demonstrations to help you understand a couple of the concepts. And so please make sure that you watch this all the way through. You will probably want to expand this if you're watching this on a computer or an iPad or something to full screen. You don't want to watch this just in a little tiny window because I'm already a little tiny there in the corner. Hi, everybody. And you'll want to be able to see some of the demonstrations. First question is, what is glass? Okay, what is glass made of? What is glass itself? And so first thing to think of is its state. Is it a solid, a liquid, or, I mean, it wouldn't be a gas, I would imagine, but is it a solid or a liquid? And the answer to that is yes. Now, it's real popular here recently for people to say that glass itself is a liquid. Because there was some research and stuff that was done where they found in old buildings, especially like a couple hundred years old, that glass panes were thicker down at the bottom. And so the thought was that glass is a liquid, that it must over time very slowly slide down. Now, that's a good evidential proof, and I actually believed that up until relatively recently, that I thought that there were liquid properties to glass. And there are. We'll get to those here in just a second. But the best way to describe glass is that it is a solid, and it's something that we call an amorphous solid. And the reason that it's called amorphous is amorphous means just kind of chaotically put together, and so the particles in it, the atoms in it, are arranged in a random fashion. Most solids are in a crystalline shape. Okay, so you see that there is some order to it. Okay, so most solids fit into this category. Now, when you have something like glass, since glass is actually made up of a lot of different materials with a lot of different compositions, it is more along the lines of something like, let me actually try to see if I can get this flat. Good enough. It's not going to be square. But it would be something more along the lines of this, where there would be kind of a random arrangement of atoms and molecules. So instead of something nice and ordered, okay, that's more crystal-like, you would have something a little bit more random, like this. And so, because of that, if you were to break a crystal, it has, which these magnets don't exactly break all that well, it would, when you break a crystal, it generally breaks at the crystal points where it meets, and so you have all these even pieces that would happen. And so that's why when glass breaks, it breaks into large pieces, small pieces, and kind of shatters all over the place, because it has this random nature, and so when you break it, it just kind of goes into a million little pieces. So glass has a lot of different compositions, and we're going to look at that. There's not just one particular formula for glass. This is how glass is made. First, you take sand. Specifically, you'll take silicon dioxide, also known as silica. You need to know silicon dioxide for sure, that is the main portion of glass. Okay, it's generally about 3/4 of glass is made out of silicon dioxide. Then you take something else like lime, which is calcium oxide, and what this does is it stops the glass from becoming soluble in water, so it won't dissolve. And then you add other agents that are generally all oxides, like sodium oxide, and that reduces the melting point because you have to heat this up a lot to be able to make glass. There's three main categories. I do want you to know each of these. One is the formers. This is the bulk of the glass, like I said, the silicon dioxide, and so that is what makes it most of it. Then there's the fluxes. That's what you add to change the melting point, okay, like silicon carbonate or something we call potassium carbonate. And then there's the stabilizers that help keep the glass strong, like calcium carbonate. So formers, bulk of the material; fluxes, change the melting point; stabilizers, keep it strong. Okay, easy to remember. Raw materials are all oxides, as we just said. It's silicon oxide. We have, phosphorus pentoxide, a couple of different things, boron trioxide. All of these here, where we have sodium oxide, calcium oxide, potassium oxide, magnesium oxide, aluminum oxide, these are all things that are used in the percentage of glass. Okay, this would be the formula here down at the bottom. This would be a good recipe for what we call soda lime glass, which it actually has nothing to do with the fact that it's a soda bottle, but a lot of glass bottles are soda lime glass, and windows are soda lime glass, and so that would be a good percentage breakdown of it. Now, here's some of the other types of glass. Obsidian. This is, if you've ever seen kind of black, kind of oily looking glass, okay, that would be obsidian. It's formed when a volcano erupts, okay, just the heating and cooling of the silicon dioxide or that's produced, while during an explosion, the heating and the cooling would cause obsidian to form. Soda lime glass. This is most common glass. We already talked about it, and most things that you see are going to be made out of soda lime glass. Leaded glass. What we call this, we generally call leaded glass crystal, but remember, it's not a crystal. This contains lead, and so it makes it real dense and heavy. It makes it real sparkly and shiny as the light goes through it because of the density of the lead. And so generally, if you have someone who has like a fine crystal glass, like you might have someone who has, who either has like really nice wine glasses, okay, and you can tell that those are leaded crystal, okay. Other places that you might see it is sometimes there's like the, what is it called, like the Swarovski or something weird like that in Russian sounding, that is little crystal figurines. Those are leaded glasses, so they have lead in them, makes it denser, and light really makes those shine as it goes through it. Tempered glass. This is where you're going to see generally on automobiles on side and rear windows. It's real strong. See, what they do is they heat up the glass during the process of creating. They heat it up and they cool it down several times. And what that does is, when it takes moisture out of the glass, but also it packs in the molecules real tight, and it makes it a stronger glass. When it does break, since it's a little bit more crystal-like, it does have the tendency to break in little pieces, and so, which is good because you don't want big giant shards of glass in an automobile accident. And so that's why, that's why in an accident you won't necessarily just see tiny pieces or shattered glass all over the place. And so windows, side windows and rear windows of cars are tempered glass. Just think about that it makes it real strong. Other type of automobile glass is laminate glass. And what they do is they actually take two sheets of glass and they have a real thin layer of plastic in the middle to strengthen it. And what that does is, since the glass is sandwiched with this plastic, is if you get into an accident, the glass doesn't just shatter and go everywhere. It actually sticks, and this plastic helps absorb some of the impact, and so it keeps the glass all together. And so that's why, if you've ever seen, like on a movie or something, someone goes and hits the windshield of a car, it takes them like 10 different times to bust through it because it's dispersing all of that impact over and over again, and using this plastic film. Okay, when you analyze glass, there's three different areas here of investigation and analysis. You find it, you measure it, you compare it. Okay, so individual characteristics. You would think that if you got to a crime scene, you would easily be able to determine where glass came from because you can just fit it together like a jigsaw. Well, the problem is that most glass doesn't just break easily where you can do that, and it gets scattered all over the place and moved around, and so it would take forever to actually do that, and even then it wouldn't necessarily be very individual in its characteristics. And so seeing that it's generally not the case that you have a lot of individual characteristics. They don't fit together well. Comparisons, require piecing together irregular sides of broken glass, and so it doesn't fit together as easily, because if you have any of it kind of grind up, then you aren't able to fit it together. And so generally you can't use a lot of individual characteristics for glass, but you can do a lot with class characteristics. This is generally how glass is used. You would need to know that for a test. And so since glass has a lot of different recipes for it, you can use that as class evidence depending on what the glass is made out of. And so you can use trace elements in the glass. You can also use things which we'll learn about in just a second, like the density and the refractive index that would be specific to that kind of glass, and you can match that up with your source. Remember, that would be comparison evidence. And so just remember class evidence, or that glass has more class characteristics than individual ones. Now, density. You should know what density is. It's how much matter you have or how much mass you have in a given volume. Okay, so density equals mass divided by volume. And so this is a way that you can actually measure glass fragments. Now, one way that you can do this, and I don't have a full example of this, but if you've ever seen like a density column here where we have water down here at the bottom and we have vegetable oil at the top, because water is more dense, it has more molecules packed together than the vegetable oil does. And so one way that you can test the density of glass is you can add it to an already dense liquid. And so there's an example here of bromobenzene. It's a dense liquid, and you add that and the glass would drop down to the bottom. Then you can add a really super dense liquid called bromoform, and it changes the density of the liquid. You add it drop by drop, okay? And at some point when you match the density of the glass, it would raise up to the middle and float in the middle of the glass, or in the middle of the liquid, okay? And so when that happens, you then know, depending on what your density is of your liquid, what the density of the glass is, and then you can match it up, okay? We might even do some flotation stuff if I can get some things together for that. Refractive index. This is very important that you know refractive index. This measures how much an object slows light down. Anytime light goes through something, even if it's clear, it slows it down a minuscule amount. Okay? And so that changes the way that you can see that light through it. And so everything that light can go through has its own refractive index. And refractive is kind of like the light bouncing off of it. Now, hold on just 1 second. Yay for awkward breaks in the video. I had someone come in who needed to ask a question. Okay, so light passes through, and that causes refraction. It causes light to bend. That's why, like when you're underwater, when light's going through, it causes things to seem bent. And so, like you have a beaker here with the straw. Well, the straw is not actually bent, but the light is bending around through the water, and so the refractive index causes the straw to appear bent. Okay. Every liquid has its own refractive index, and so if a piece of glass is placed in a liquid with a different refractive index, then you can see the glass. So, like, let's see if it's gonna, yeah. Let's say I take my beaker of water here, and I take a little bit of broken borosilicate glass, and I put it in there. You can actually still see the glass, okay? Do you see that? You can see the outline of it. You can even, if you, and I don't know how well this is going to translate through webcam, but you can even see a little, like, kind of halo of light around the glass that allows you to, actually allows you to see the glass. That's called a backline, where you can still see the outline of the glass, a little halo of light around it. Now, when you have a liquid that has a similar refractive index as glass, something like this happens. The backline disappears. And so when I take something like vegetable oil and I put the same, let me get the water off of it, and I put the same piece of glass, and of course the water on it has ruined my demonstration here. When you put it in, it seems to make it almost disappear. Okay, now this vegetable oil doesn't have the exact same refractive index, and you can even see where some of the water is still on the glass. Okay, I guess you can possibly see it. But when you add it in, it almost disappears. You can just see a very faint outline of the backline. Okay, that's because they have similar refractive indexes. They bend light the same way. Okay. Now, let's talk about glass fractures a bit. Glass is actually a little bit elastic, okay? That's why every time you shut your car door, it doesn't just shatter, okay? There's a little bit of elasticity in it. However, when that elastic limit breaks, glass breaks, okay? And it's not going to be put back together, i.e. Humpty Dumpty. And so, let's talk about types of fractures. I'm going to draw you a little picture here. First one you need to know is a radial fracture. It is produced first. So, you shoot a bullet through a window, okay? The first thing that happens, like my bullet hole, Um, the first thing that happens is a radial fracture. And think of that as a radius that comes out. It looks like a spider web. And so from the middle where this bullet comes out, you have a radial fracture takes place. Now it actually forms on the other side of the hole. And we'll talk about that. But so these lines are actually breaking on the other side of the glass where the bullet went through. And so this all, and we'll talk about how it always terminates into an existing fracture. If you have any cracks in the windshield of your car, okay, if you have like a little star where something has hit it, and you have another one over here, and it starts, after a while, it starts to kind of like slide over and gets longer, it's ultimately going to end in that hole that started first, okay? I have one across the front of my truck where I had someone kind of ding the front part of the glass, and then ding the other side of the glass, and it crawled all the way across the windshield, and it met up. The radial fracture did. Okay, then what you have is you have concentric. Okay, so think of circles. These all form and they encircle the bullet hole. And so as the glass breaks, it starts to look like this. You have your radial fractures, then you have your concentric fractures. Okay? And so these are always on the same side of where the bullet went through or wherever the force came from. And so radial is on this side of it, okay? And concentric is on this side of the glass. Now, when it comes to determining the sequence of multiple bullet holes, because let's say that over here you have some other radial fractures. Actually, radial and concentric fractures. What's going to happen is these radial fractures are going to meet up with other radial fractures. Just like I was saying, you can tell that this was shot first because these radial fractures reach out and cross into the radial fractures on the second bullet hole. Okay, does that make sense? And so if it, you're not going to have where this comes down and meets over here. Okay, and so that's how you can tell if a fracture, kind of attaches to another radial fracture, then this one came afterwards, and so that helps you to determine which ones happened first. Now, determining the direction of which way a bullet was fired, the larger side of a hole, like through glass, is always on the exit side, and this is because when you have, I don't think I'm going to be able to draw this well. Okay. When you have a bullet, that's a horrible drawing, by the way. When you have a bullet going through a pane of glass, it actually pushes out this kind of pyramid shape, okay, this kind of cork shape piece of glass, and so the side that the bullet goes through, the exit point, is always a larger hole than the entry point, okay, because it pushes out this large piece. And so that's one way that you can tell is you can determine the size of the entry hole to the size of the exit hole. And also there's some things about glass, since it is elastic. And so if you have your bullet going this way, it's going to cause that glass to go out and then buckle back. And so glass tends to actually fly forward. Okay? And so if I'm firing the bullet this way at you, the glass is actually going to fly you're going to find more glass on this side than you are on the other side. And so that's really important in determining that. Okay. And final things with collecting glass evidence. You need to first photograph it. Don't touch anything until you have photographed it and you have identified it. Collect large fragments first. Those are going to be the most important. You need to make sure that it is identified and marked which side was the inside and outside of it, because that would get real confusing quick when you're trying to put that back together in a lab or in a criminalistics lab. And so you also need to determine and try to diagram out where it came from, what windows were there. Let's see. You need to note if there's any blood or trace evidence at all that's on the glass fragments. You need to make sure that you package it all very well, and you need to to separate the glass out, if you have glass that's clear over here, you have glass that is black over here, you need to make sure that you separate that out, and so it can be tested properly. Keep them, like I just said, keep them separate, especially if they might be two different sources. Keep them away from everything else. And let's see. Yeah, and so I mean basic rules that we've been talking about with gathering evidence. And that is pretty much it for glass analysis, and for the most part, other than some of the stuff you're going to be teaching in your lessons, what you need to know.